lesson is over equilateral and isosceles triangles. Let's look at each of these types of triangles. In an isosceles triangle, you may have heard in middle school isosceles 2 days ago. That's just a little saying, a little reminder that two sides of an isosceles triangle are congruent. And those two congruent sides are called legs. Opposite each of those legs is an angle, okay? Those are called base angles, and those angles are congruent. So the base angles, you might refer to them as opposite of the congruent sides. And then where those congruent sides meet, that is called a vertex angle. And now an equilateral triangle, it's kind of a special isosceles triangle because we can actually classify every equilateral triangle as isosceles. Because what do you need to be an isosceles triangle? You need two congruent sides. Well, an equilateral triangle satisfies that requirement. But more so, an equilateral triangle has three congruent angles and three congruent sides. So if an isosceles triangle has two congruent sides, an equilateral triangle also has two congruent sides, right? These sides are congruent, these sides are congruent, these sides are congruent. So it satisfies that requirement. It's kind of like every square can be classified as a rectangle, but not every rectangle can be classified as a square. Every equilateral triangle can be classified as an isosceles triangle, but not every isosceles triangle can be classified as equilateral. So let's get into the theorems that we're going to be using today. The first is the isosceles triangle theorem. And I want you to really pay attention to what the hypothesis is, right? It follows if this, then the conclusion follows that. The isosceles triangle theorem states, if two sides of a triangle are congruent, then the angles opposite the sides are congruent. So if two sides are congruent, then the opposite angles are congruent. Let's look at the image we're given in our hypothesis. Triangle ABC has two congruent sides. So if we have two congruent sides, then we have two congruent angles opposite those sides. Those base angles are congruent. So angle A is congruent to angle C. Now the converse of the isosceles triangle theorem, what do you think? Well, we're going to switch our hypothesis and conclusion. So now, not if two sides are congruent, if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So now let's look at this triangle. Triangle DEF, we're given two congruent angles. Well, we can then conclude that the sides opposite of those angles are congruent. So segment DE is congruent to segment EF, I'm sorry. Then we're going to look at the equilateral triangle corollary. Now, a corollary is just a theorem, so you can refer to it as a theorem, but it just follows, it easily follows another theorem. That's what a corollary is. So the equilateral triangle theorem easily follows the isosceles triangle theorem. Or the corollary or theorem, you can call it equilateral triangle theorem, equilateral triangle corollary. If a triangle is equilateral, then it is equiangular. So if all sides are congruent, all angles are congruent. So if I'm given three congruent sides, I know angle A is congruent to angle B, which is congruent to angle C. All angles are congruent. Now the equiangular triangle corollary, we're going to switch our hypothesis and conclusion. If a triangle is equiangular, then it is equilateral. So we're given a triangle that has three congruent angles. We can conclude then that it has three congruent sides. So segment DE is congruent to segment EF, which is congruent to segment DF. So let's move on and look at some proofs. We're going to prove the isosceles triangle theorem. In example number 1, we're given a triangle that shows two congruent sides. And we're given, it's written here, that segment AB is congruent to segment AC. We're also shown that in our figure. We don't necessarily need that in both. If it's given here, that's enough. If it's given in our figure, that is also enough. We're asked to prove that angle B is congruent to angle C, which is what the isosceles triangle theorem states. So first, let's write our given. We're given that segment AB is congruent to segment AC. And now I'm going to do something that we haven't done before. We're going to draw P. That's going to be the midpoint of BC. And that's my statement. Draw point P, which is the midpoint of BC. And our reason is going to say that every segment has a unique midpoint. Okay, we know that to be true. That's going to be our reason. And then the next thing that we're going to do, I didn't ask you to fill it in because, again, we haven't done steps 2 and 3 before. We're going to draw the auxiliary line AP, and our reason's going to be through 2 points, there is exactly one line. So I can draw a midpoint on a figure, and I can draw a segment that connects 2 points. Okay, so through 2 points, there is exactly one line. We know that to be true. Now, I know from the definition of midpoint that a midpoint separates a segment into 2 congruent segments. So my statement is that segment BP is congruent to segment CP, and my reason here is that is the definition of midpoint. Now, I drew this auxiliary line here, and it split this triangle into 2 triangles. All right, and we've seen in previous lessons that using the reflexive property of congruence, I can say that a segment AP is congruent to itself. Right, so segment AP is congruent to segment AP by the reflexive property of congruence. What have I just done in my figure? I split that triangle into 2 triangles, and I have now shown you that they are congruent triangles. So my next statement is going to be that triangle ABP is congruent to triangle ACP. And what's my reason? Side, side, side. And now we just did this in the last lesson, but once we prove 2 triangles are congruent, we know that all pairs of corresponding parts are congruent. So I can then conclude in my next step that angle B is congruent to angle C by CPCTC. And that's the isosceles triangle theorem, right? If I have 2 congruent segments, then the angles opposite those segments are also congruent. In example number 2, we're going to prove the equilateral triangle corollary. Again, it's just a theorem, but it follows very nicely the theorem that we just proved. So that's why it's a corollary, but we can call it a theorem, okay? So in example number 2, we're given that segment AB is congruent to segment BC, which is congruent to segment AC. So we're given an equilateral triangle. We're asked to prove that all of these angles are congruent. So first, let's state what we're given. We're given that all of these sides are congruent. Now, what we just showed is that I have in the isosceles triangle theorem, if I have 2 pairs of corresponding, or not 2 pairs, if I have 2 sides that are congruent, I know those base angles or the angles opposite those sides are also congruent. So when I'm looking at this triangle, could I say that segment AB is congruent to segment BC, and so that angle A is congruent to angle C? Could I say that, segment AC is congruent to segment BC, so that means that these 2 angles are congruent? I can, and that's exactly what we're going to do. We're going to show that angle A is congruent to angle C by the isosceles triangle theorem. Because if these 2 segments are congruent, then these 2 angles are congruent. And guess what? In the next statement, we're going to do the exact same thing, except we're going to do this with angle A and angle B. So in angle A, and if angle A is congruent to angle B by the isosceles triangle theorem, because look at this, segment BC is congruent to segment AC. So we're using this theorem in the next theorem or corollary. We use the isosceles triangle theorem to show two base angles are congruent when two sides are congruent. So now we have now proven, right, that angle, oh, looky here, I need to redo this. Statement number 4 should say, and you need to change this and write this down, we need this up here. Angle A is congruent to angle B, which is congruent to angle C. So I want you to write that down right here. And let me see if I can do that with my pen, actually. I'm going to do that. We'll do that. This right here should be angle A is congruent to, oh my gosh, I'm sorry, angle B, which is congruent to angle, angle C. Okay, that doesn't look very good, but that's what it should say instead of that. And how do we know that? We know that by the transitive property of congruence. So let's look at 2 and 3, right? If angle A is congruent to angle C and angle A is congruent to angle B, then I know that angle C is congruent to angle B by the transitive property of congruence. And so they're all congruent to one another. All right, let's move on. And now we're going to use the properties that we've just discussed to find the missing values. And I'm going to go fairly quickly through this. And if you need to pause the video, rewind it so that you can do some algebra on your own, I would encourage that. In example number 3, we are given that triangle. Actually, I think that should say example number, yes, that should be example number 3. Okay, we are given that triangle ABC is isosceles. We're asked to find x. All right. Well, if I know that triangle ABC is isosceles, then I know that angle A is congruent to angle C, which means the measure of angle A is equal to the measure of angle C. I can then set these two expressions equal to one another and solve for x. And we're going to do that. So I'm going to write 10x plus 2 equals 11x minus 3. I'm going to solve for x by subtracting 10x from both sides. And I'm left with 2 equals x minus 3. I'm then going to add 3 to both sides to get that x equals 5. And I can write it just right there. X equals 5. Moving on to example number 4. Triangle MNO is equiangular. Find x. If it's equiangular, that means all the angles are congruent. And I know that angles in a triangle add up to 180 degrees. And 180 divided by 3 is 60. So each of these angles measures 60 degrees, which means the measure of angle M is 60 degrees. And now I can replace the measure of angle M with 9x minus 3, which is that expression. And now I'm going to solve for x. I'm going to add 3 to both sides, and I'm left with 9x equals 63. I'm going to divide both sides by 9 and get x equals 7. Let's move on. Example number 5 says, triangle JKL is equilateral. Find x. Again, if it's equilateral, what does that mean? All the sides are congruent. If the sides are congruent, then their lengths are equal. So I know the length of JK is equal to the length of KL. So I can set those two expressions equal to one another. 6x minus 12 equals 4x. I'm going to solve for x by subtracting 6 from both sides. I'm left with this step right here, which is negative 12 equals negative 2x. I divide both sides by negative 2, and I get that x equals 6. And I got 6 on this side, 6 equals x. I can just rewrite it, x equals 6. I tend to like the variable on the left. I just do. But that's, again, a step you do not have to rewrite, but I like to do that. In example number 6, we are given that triangle ABC is isosceles. Now we're asked to find the measure of angle B. So be careful with what you're asked to find. We have been asked to find the value of the variable. Now we're asked to find the measure of angle B. But we do first need to find the value of the variable. So this is going to add an extra step. If I know this is an isosceles triangle, I know those base angles are congruent, which means their angle measures are equal to one another. So Angles are congruent, so the angle measures are equal to one another. I'm just going to write measure of angle A is equal to measure of angle B, and I'm going to substitute each expression into my equation. 4x plus 11 equals 6x minus 5. I'm going to solve for x by subtracting 4x from both sides. I'm left with, I'm at this step right here. Oh my gosh, I just can't write very well like this. Sorry. I'm at that step right there. 11 equals 2x minus 5. I'm going to add 5 to both sides, and I'm left with 16 equals 2x. Divide both sides by 2 to get x equals 8. We're not done. We're not asked to find what x equals. We're asked to find the measure of angle B. So now the measure of angle B is up here, right? It's 6x minus 5. So what am I going to do? The measure of angle B is 6x minus 5. I'm going to substitute 8 in for the value of x. So instead of 6x minus 5, I'm left with 6 times 8 minus 5, which is 48 minus 5, which is 43. Therefore, the measure of angle B is 43 degrees. Let's look at our last and final problem. Number 7, we are asked to find the measure of angle D. And we're going to work through this entire figure to see if we can find the measure of angle D. We're only given that triangle AEB is an isosceles triangle. Triangle BCD is also an isosceles triangle. We're given that this vertex angle up here is 108 degrees. So I know because it's an isosceles triangle, these two base angles are congruent. Let's label those X. And I've labeled them the same thing because their angle measures are equal. So I know that angles in a triangle, their angle measures add up to 180 degrees, which means X plus 108 equals 180 degrees. That means 2 times X plus 108 equals 180. I've now set up an equation with one variable so I can solve for the value of the variable. I'm going to subtract 108 from both sides, and I'm left with 2x equals 72. When I divide both sides by 2, I get x equals 36. I've now found the value of the variable, which I've already labeled to be each one of those angle measures, which means here's a triangle, an isosceles triangle. The vertex angle measures 108 degrees, and each of the base angles measures 36 degrees. Let's move on to this next triangle. Now we know that this angle measure right here is 36 degrees. Its vertex angle is right here, right? Angle CBD is that vertex angle. I know vertex angles are congruent, which means this angle is also 36 degrees. Now in this little triangle over here, triangle BCD, I have another isosceles triangle. And again, I've now have the angle measure for that vertex angle. But because it's isosceles, I know that these two base angles are congruent, which means their angle measures are equal. I'm going to label those a different variable. I'm going to label each of those y. I now know, doing the same steps with this little triangle, that all the angle measures in a triangle add up to 180 degrees. So y plus 36 is 180, which means 2y plus 36 equals 180. If I subtract 36 from both sides, I'm left with 2y equals 144. When I divide both sides by 2, I'm left with y equals 72. And I've labeled both of those angles to be y, which means the measure of angle D is 72 degrees. And that concludes your notes over isosceles and equilateral triangles. I hope it was helpful.